In this chapter, we are studying exponential functions, so that is functions of the form a to the power of x. We have a base number a that is fixed, and then our exponent is the variable x. We are going to consider this for values of a that are positive and different from 1. And let's see why these restrictions actually make sense. If the base a is equal to 1, then we are considering 1 to the power of x, and this is always equal to 1. So this is not a very interesting function, it's just a constant function equal to 1. If we consider a to be equal to 0, then when we try to find the value of 0 to the power of x, we have two different cases. If x is not 0, then 0 to the power of x is 0. But when x is equal to 0, this value is not even defined. So again, this is not a very interesting function to study. If we consider our base to be a negative number, then we run into all kinds of problems. Let's take a look at the case where we consider the base to be minus 2. So, for instance, let's try to do what is minus 2 to the power of 1. Well, this is just minus 2, which is a negative number. But then when we do minus 2 to the power of 2, this is 4, which is a positive number. So what is happening is that this function will be jumping up and down depending on the parity of the exponent if we are talking about natural exponents. So this jumps up and down. But this is not the worst thing that happens to this function. If we try to do minus 2 to the power of a half, this means that we are doing the square root of minus 2, and this does not exist. So there will be many points where the function is not even defined, so we stay away of the case a less than 0. So once that we agree that our base is going to be a positive number and different from 1, let's check that we actually know what it means when we say a to the power of x. And there are different cases over here. If we are talking about x being a natural number that is greater or equal than 1, so we are saying a to the power of x, for instance, could be a to the power of 15 or a to the power of 100. What we're saying here is that we need to multiply a by itself as many times as the exponent, so x times. So this we know how to do. If x is exactly 0, we saw in class that it makes sense to define a to the power of 0 to be equal to 1. If x is now an integer, so it's either one of the natural numbers or the negative of the natural numbers, well, then in this case we need to say what it is a to the power of a negative number. So let's say a to the power of minus n when n is a natural number and n is not 0. We already know how to do a to the power of 0. So what I'm doing over here, this would be like finding what is a to the power of minus 4, for instance. And the definition for this is that this is the reciprocal of a to the power of n. So far, we know how to do a to the power of x if x is an integer number. The natural numbers are inside, so I don't need to mention that. What now if x is a rational number? What if we need to do, let's say that x, let's begin by saying, is a number of the form m over n, where m is a natural number and n is a natural number but different from 0, so it makes sense to divide. Let me be a little bit more ambitious even here. Let me say that my value m here could be even an integer. So when we try to do a to the power of m over n, this is defined as being, we have two options. Well, we can say that we are taking the n root of a and then we are taking the m power of that, or that would be the same as doing a to the power of m first and then taking the nth root of that. So here we could be doing something like, for instance, a to the power of minus 3 over 2. So we could be doing the square root of a, and then we could be considering all of this to the power of minus 3. Note here that we are considering a to be a positive value, so we are not going to have problem taking square roots or fourth roots of any type of roots, because we already know that we have a base that is a positive number. If our variable x takes values that are real numbers that are not rational, so here I'm saying that my x belongs to a set of real numbers, but it's not a rational number, so it's not a fraction. We know numbers like this. For instance, we know x could be square root of 2, that's an irrational number. It could be pi, it could be square root of 5, oh, it could be e. Deciding what it is, in this case, a to the power of x, is quite complicated, and it's not something we can do with the tools that we have right now. But let me just try to give you an idea of what we are going to do. Let's say we're trying to say what is a to the power of pi. So here we have the value pi, and we know that pi has an infinite non-periodic decimal expansion that starts with 3.1415, and it continues going. So what we will do in this case is, well, we don't know how to find a to the power of pi, but we know how to find, for instance, a to the power of, let's say, over here I'm going to write the number 3.14. And then we can also find how much is a to the power of 3.141. Those are rational numbers, right? Like in the worst case, we can write 3.14 as 314 divided by 100. So those are rational numbers. We can continue doing that. So we can truncate the decimal expansion of pi, and those truncations, they give me rational numbers. And for those rational numbers, we're in the previous case, so we know how to find a to the power of that number. So we keep doing that for numbers that are closer and closer and closer to pi, and the idea is that in that way we are going to also find what is a to the power of pi. Now, all the same, maybe this sounds very weird to you. You don't need to completely understand what's going on, because next year we are going to understand what sequences are, and then this will make much more sense. But in any case, you can go to your calculator and ask your calculator how much is, for instance, I don't know, 3 to the power of pi, and your calculator will know what the answer is. So to sum up, we know what are the conditions for defining the exponential functions we are going to consider. We need a base to be positive and different from 1. And then when we want to find what is a to the power of x, we can find what that means. We have a definition of what that means for values that are rational. And of course, inside the rational values, they are included the integers, and inside the integers are included the natural numbers. And you are going to have to believe that if what we have for the variable is an irrational number, so a real number that is not rational, there is also a definition of what this means that makes sense and will make more sense for you in the future.